Hello everyone, we are Group 4 from J4CE MEM360 and this is our workshop project on fabricating a peristaltic pump. Let me introduce our team.
Cover an introduction to the peristaltic pump, the safety equipment and techniques we use, a step-by-step walkthrough of our manufacturing process, cutting, lathe, milling, drilling, tapping and surface finishing. Also the problems we face during fabrication and how we solve them, our discussion on possible improvements, and finally our references. A peristaltic pump moves fluid by compressing a flexible tube using rotating rollers, which push liquid through the tube without the fluid ever touching the pump mechanism itself. This makes it ideal for applications requiring hygiene or contamination control, such as medical dosing, food processing, and laboratory fluid handling.
Before starting any machining work, safety was our top priority. Here is the personal protective equipment we used throughout the project.
The first step was cutting our mild steel round bar and flat stock to rough length using the saw. We cut pump housings blank, slightly oversized to allow for facing on the lathe, and cut roller brackets flat bar to approximately 47 mm length before milling to final shape.
For technique, we always confirm that workpiece was clamped securely before starting a cut. Check spindle speed and feed rate against the material. Before machining, keep our hand clear of cutting part and never left a running machine unattended. We also brief with our lab instructor before every session, following the lab schedule for CNC lathe code and machining handling.
Next, we turn pump housing on the lathe. We face both ends to lathe, turn the outer diameter down to 50 mm, then bore the inner cavity to 45 mm and a depth of 9 mm to house the rollers and bracket. We also turn the central through hole for the 14 mm shaft bore and face the 21 mm overall body height.
During the machining process, the diameter was measured regularly using a vernier caliper to ensure dimensional accuracy. Proper cutting speed and feed rate were maintained to achieve a smooth surface finish while ensuring safe machine operation. After completing the turning operation, the workpiece underwent the drilling process using the lathe machine. A center drill was first used to guide the drill bit and prevent it from wandering. The hole was then drilled to the required depth and diameter based on the design specifications. For this housing part, the diameter required is 14 mm and it will cut through all 21 mm of the housing part length. Next, the single point triangle cutting tool was clamped into the two posts on a lathe machine, and then the workpiece will be held in a 3-joint chuck, spinning while the tool cuts into it. As the lathe machine spins the material at high speed, the tool advances steadily, shaving away thin layers of metal to shape the surface. You can see the fine spiral chips flying around left behind on the workpiece. As the workpiece rotates rapidly in the chuck while the cutting tool mounted securely on the tool post, it moves along the feed direction to remove material layer by layer. Next, we proceed to bandsaw cutting by clamping the material onto the clamp so we can proceed to bandsaw cutting. All three members cooperate throughout this process. This process removes the metal from the excess material. After the bandsaw cutting process was done, we realized that the hole didn't cut through all the way of the housing part length, so we proceed to another drilling once again. Here, we perform step turning, reducing the workpiece the outer diameter along a marked section. This creates a precise seating surface designed to fit a bearing. These steps ensures the bearing sits at the correct depth and is properly located along the shaft, which prevents axial movement once assembled. Since sun-blasting equipment wasn't available to us, we surface finished both parts by manual grinding instead. We use a handheld grinding tool to remove burrs and sharp edges left from milling and drilling, then followed up with finer grinding to smooth out tune marks on the outer surfaces before assembly. Other than that, we also fully utilize the use of file and hand grinder to smooth out and give the best surface finish. As a preparation before drilling, we use a hammer and a center punch to mark the perfect place we want to drill. This gives us the best perfect spot to drill.
We drill the pilot holes. The three with 5 mm diameters roller pin holes on part 2, the 6 mm diameter mounting holes and 8 mm clearance hole on part 1, and the pilot holes for our M6 tape holes. Once the holes were drilled to the correct tapping diameter, we hand tap all M6 times 1 thread holes on both part 1 and part 2. We then move to the milling machine to shape part 2. The roller bracket, cutting the slot profile with two radius 7.5 mm rounded ends and machining it to its final 45 mm by 30 mm outline. On pump housing, milling was also used to cut the side slot and locate the mounting holes around the housing wall.
With both parts machined, we assemble the pump by pressing the 6 to 6 zigzag bearings onto the roller pins, fitting the bracket assembly into the housing bore, securing it with the M6 countersink screws and closing the housing with the pen head screws, hex nut, nylon lock nut and flat washer. The silicone tube was then routed around the rollers to complete the pump.
During fabrication, we face several challenges. Here are 5 of them and how we solve each one.
Our first problem came around when the housing part actually fell and dented at the edges, so we carefully used a hammer to tap this affected area surface back again. And then our second problem is our drill chuck kept coming loose, so we called out to the assistant engineer to retighten the chuck firmly again. And then our third problem is that the clamping screw of the cutting tool came loose, causing the insert to fall around out of its position. So again, we called out to assistant engineer to resecure it into the holder again. Our fourth problem is some parts during the assembly did not fit perfectly, which is due to the factor of measurement details. So as a solution, we remeasured and do some minor machining process again. Lastly, our fifth problem is that the raw material that cut during bandsaw cutting was slightly larger and longer than the actual measurements, so we had to redo it again. Reflecting on our fabrication process, there are several improvements we would like to make in future iterations. Number 1, we would like to do a careful planning and verifications of dimensions, which helps us to reduce errors and reduce material waste, because frequent marking and dimensional inspection actually cost us time and energy. Secondly, a proper selection of cutting speed, feed rate and cutting tools, which helps us to improve machining quality and gives us the best surface finish from a regular maintenance of workshop machines and the use of sharp cutting tools. Thirdly is better teamwork and communication. Better teamwork could provide work efficiency, which also saves time and energy from doing repeated works. This ensures that each member clearly understands their assigned responsibilities during the machining sequence. Last but not least is to conduct a trial assembly before a final assembly. Our mistake is doing the final assembly, then we find out that we have an error, so we had to redo it again and ensure a smoother operation, which is one of the best advantage.